Hi everybody. In this video, I am going to be solving and discussing one of my favorite problems of all time that you see on this board. It came up in the IMO 1976 exam, the International Math Olympiad in 1976. And the reason I like it so much is that when you first think about this problem, it looks very complicated, very difficult to solve. But there's a very simple, very elegant line of reasoning that you can use to solve this. And that line of reasoning is actually something even a fifth grader can understand and actually solve the problem with. So that's why I love this problem. Looks complicated at the outset, but has a very elegant solution. So let's look at what the problem says. Determine the largest number, which is the product of positive integers with sum 1976. So imagine a bunch of integers that have the sum 1976, and now think about their product, and you have to find the maximum possible value of that product. So that's really the problem. And before you go forward, just play around with this a little bit, try to figure it out on your own, so that when you actually go through the solution that I'm going to discuss, you can appreciate how elegant the solution is. Okay, so let's dive right into it. This number 1976, there seems to be nothing special about it really, except for the fact that it seems to be related to the year 1976 in which this problem came up. So let's actually investigate this problem with a much more smaller or simpler number. So let's say we had the number 20. So let's take n equal to 20. And now let's imagine a certain set of integers, positive integers, which sum to 20. And we have to find the maximum possible product of such a set of integers. So here's what I'm going to do. I'm going to start with a set of integers that sums to 20. And the simplest possible such set is just the set with the single element, that's 20. And I'm going to look at the product of the elements in this set. So in this case, the product is just 20 because I just have a single element. And now what I'm going to do is I'm going to try and split the elements here, in this case 20, and see if I can increase the product in the next step. So for example, if I split 20 as 1 and 19, that doesn't really help me because the product actually goes down. So originally I'm starting with the product 20, but with 1 and 19, the product of those two elements becomes 19, which is smaller than 20. So that doesn't work. But what if I split 20 as 9 and 11? So if I split 20 as 9 and 11, this works because I have managed to successfully increase the product. From a product of 20, I now have a product of 9 times 11, which is 99, which is greater than 20. While the sum still stays the same. The sum is still 20. So this is what I'm going to do step by step. At every step, I'm going to try and split the elements that I have, and I'm going to see if I can increase the product by doing that. So let's look at 9. Can I split 9 in a way where the overall product of all the elements in the set increases? So if I split 9 as, let's say, 1 and 8, that doesn't work because the product goes down. The product of 1 and 8 is actually smaller than 9, so my overall product will go down. But if I split 9 as, let's say, 4 and 5, that should work because 4 and 5 have a product of 20, which is greater than 9. So my overall product will increase. Similarly, I could split 11 as, let's say, 3 and 8. And that would also work because 3 and 8 have a product of 24, which is greater than 11. So if I take this set now, this set in my third step now still has a sum of 20, but the product has increased further. Okay, now let's keep going. And let's see what is the maximum simplification we can do to this set in which the product is the maximum possible value beyond which you can't go any further. So what can I do with this 4? So I could split it as 3 and 1, but that would decrease my product. Or I could split it as 2 and 2, and that would keep my product the same because 2 and 2 have a product of 4. So let's actually just do that. While it does not change the product, it actually just gives me a simpler set of elements versus 4, a smaller set of elements versus 4. So I have 2 and 2 here. What about this 5? So can I split this in a way that my overall product increases? If I split it as 1 and 4, the product goes down because 1 and 4 have a product of 4 which is smaller than 5. So let me split it as 2 and 3. Okay, so 2 and 3. So that would increase my product because 6, 2 and 3 have a product of 6 which is greater than 5. What about this 3? Can I split this so that the product increases? If I split it as 2 and 1, the product actually decreases. So I don't do anything with it. I just leave it like that, like 3. And then what about this 8? So let's split this 8 as, let's just take a random combination. So let's say 3 and 5. Okay, so 3 and 5. And that would increase my product because 3 and 5 have a product of 15 that's greater than 8. So now in step 4, I am at this set. Okay, and now let's keep going once more. This 2, I can't do anything more with it, with any of the 2s alone, because if I split the 2 as 1 and 1, my product actually decreases. So let's just leave this as 2, 2, 2. We also saw that 3 can't be split any further to increase the product. So let's just copy over the 3s, 3, 3, 3, and then what about this 5? So I can't split it as 1 and 4 because the product decreases, but I can actually split it as 2 and 3. Okay, so now I am at this set here. And it seems to me that we have hit the end of the line and we can't go any further. So the product of this set of elements, so the sum of this set of elements is 20, and we have constructed it in a way where it seems like the product is the maximum possible value. But wait, there's a catch. You can actually replace these 3 2's here with sum to 6. You can replace these 3 2's with 2 3's. So if you replace these 3 2's with 2 3's, the sum still stays the same, but the product increases. So 2 times 2 times 2 is 8, but 3 times 3 is 9. So when you have 3 2's, you replace them with 2 3's and the product actually increases. So you have a 3 and 3, and then you just copy over these 3's. So this one, this one, this one, and this one, and then you have finally 1, 2 left, which I'm going to write here. So this is what I arrive at, and from this point onward, it seems like we can't go any further. So this is the set of elements that sums to 20 and has the maximum possible product. And if you notice carefully, this is all 3's and then there is a 2, because 20 is 6 times 3 plus 2. So you have all 3's and then you have a 2 left. And therefore, the product 2 times 3 to the power 6, because you have 6 3's, seems to be the maximum possible product of a set of elements with sum equal to 20. So the insights gleaned from this exercise are what we're going to use in now solving the actual problem. Okay, so here's what we are going to do. We are going to prove that the maximum possible product will always be something like this set here, where you have as many 3's as possible, and then there may be 1 or 2 2's like you see here in this case. So let's go about proving this step by step. So first, I'm going to prove that there can be no element in the maximum possible product that is greater than 4. So there can be no element in the maximum product that is greater than 4. And this is actually very simple to see, because if you have a number in the maximal product that is greater than 4, so let's say n is a number in that product that is greater than 4. If you split this number n as 3 and n minus 3, if you split this number as 3 and n minus 3, the product of these two numbers will actually increase the overall product. While the sum will be the same, you've split n as 3 and n minus 3, so their sum is still n, but the product actually increases. So let's try it out. So let's take 15, which is greater than 4. And if I split 15 as, let's say, 3 and 12, my product increases. So 3 times 12 is 36, which is greater than 15. So my claim is that if you split a number greater than 4 as 3, a number n that's greater than 4 as 3 and n minus 3, the product will always increase. And it's actually very simple to see. If you multiply these two numbers, 3 and n minus 3, you have 3 times n minus 3 is 3n minus 9, which is, I'm just going to take out an n because I'm trying to show that this thing is greater than n. So n plus 2n minus 9, and this is n plus 2 times n minus 4.5. And we just said that n is an integer that's greater than 4, which means that this is positive, which means that this whole thing is greater than n. So the product of 3 and n minus 3 is greater than n. And therefore, in the maximal product, you will have no element that's greater than 4, because if you had an element that was greater than 4, you could just split it as 3 and n minus 3 and you would get an even higher product. Okay, so no element greater than 4. Now next is a very simple observation where we just say that if you have a 4 in the maximal product, you can just replace it by a 2 and a 2. This does not change the overall sum, and it also does not change the overall product, but it just simplifies things in terms of reducing 4 into a simpler set of elements, 2 and 2. So that's straightforward, nothing special about that. But then I claim, in my third claim, I basically will prove that if you cannot have more than a certain number of 2's. In fact, you cannot have more than 2 2's, because if you have 3 2's in the maximal product, so if you have 3 2's in the maximal product, you can actually replace, this is not possible because you could actually replace it by a 3 and a 3, which would keep the overall sum the same, but the product would increase, because 2 times 2 times 2 is 8, but 3 times 3 is 9. So your overall product has increased, just like we saw in the example of 20 as our number. So therefore, you cannot have a situation in the maximal product where you have 3 2's, and therefore the number of 2's should be less than 3. You could have 2 2's, you could have 1 2, or you could have no 2's. Okay, so that's my claim number 3. And then number 4 is the simple claim that no element can be equal to 1 in the maximal product. No element equal to 1. Why is that? Because if you had a 1 in the maximal product, let's say you had a 1 in the maximal product, and let's say you have any other number, let's say 7, then this combination of 1 and 7 could actually be replaced by 1 plus 7, which is 8. So your sum does not change of the overall set, but your product increases. So if you had a 1, it could be combined with any other element, and you create a new element that keeps the sum the same, but the product increases, and therefore 1 cannot be in the maximal product. So no element equal to 1. So let's see what these 4 conclusions tell us. Very beautiful reasoning, and they tell us so much about the situation. What we have concluded is that there can be no element in the maximal product set of integers that give us the maximum possible product. No element is possible that's greater than 4, because you could just split it as 3 and n minus 3 and get an even higher product. Any element equal to 4 could just be replaced by 2 and 2. Any combination of 3 2's could be replaced by 2 3's, and therefore in the maximal product you would not have more than 2 2's. You could have a maximum of only 2 2's. And then finally we concluded that no element can be equal to 1, because if you had a 1, you could combine it with any other element to produce a new element that would keep the sum the same, but the product would increase. Okay, now let's apply it to our actual situation. So let's take a series of numbers as examples before we get to our actual number 1976, which we are trying to solve for. So if we take n as 20, which is our first example that we took to understand the situation, what is that set of integers which sums to 20 but also gives us the maximum product? So as we said, it should only have 2's and 3's. It should have as many 3's as possible, and the number of 2's should not be more than 2, because then you could combine them and replace them with 3's. and you can have no ones, you can have only 2s and 3s. So just remember the 4 conclusions that we drew for this situation. So the way to just find that combination is just divide this by 3 and see what the remainder is. So if you divide 20 by 3, you will find that this is simply 6 times 3. So you have 6 3s in 20, and then you have 2 left over. And this combination actually satisfies our constraints. If you take the set which has 6 3s and 1 2, so you have 6 3s and you have 1 2. So this has no 1s, this has no number greater than 4, and this has greater than or equal to 4, and this has just 1 2. So this will work as the set that will give us the maximum possible product. So the maximum possible product, let's call it P max, will be simply 2 times 3 to the power 6. So that's our answer for n equal to 20. And we also concluded that by actually splitting 20 till we got to this. Now, if I take n equal to 30 instead, now 30 is essentially 10 times 3. So 10 times 3, and you don't have any remainder left over. So if you take the set that has 10 3s, so you have 3 3 3 and you have 10 such 3s. This is the set that will give you the maximum possible product. It has no 2s, which is fine. So the maximum possible product here is 3 to the power 10. And then let's take one more example. Let's take n equal to 100, which is 33 times 3, so 99 plus 1. So 33 times 3 plus 1. So you have 33 3s and then you have a 1. But remember that in our maximal set, in the set that gives us the maximum product, we cannot have a 1. So what we'll do here is we'll take 1 3 from here and we'll write it as 32 times 3 plus 3 plus 1, which is 4. And this 4 we will write as 2 2s. So you have 32 times 3 plus 2 plus 2. So remember that we could go to a maximum of 2 2s but not have more than 2 2s. So in this case, if we consider the set that has 32 3s, so you have 32 3s and you have 2 2s. So this is the set of elements sums to 100 and it gives us the maximum possible product. So in this case, the maximum product is P max is 2 square or 4 times 3 to the power 32. Great. And now let's finally come to our actual question, which was the number n equal to 1976. If I divide this by 3, I will get 6, 5, 8 times 3, and then I'll get a remainder of 2. That's great. So I have, if I consider the set that has 658 3s and then 1 2, that set sums to 1976. It satisfies all my constraints, all the 4 constraints, and therefore that is the set that will give me the maximum possible product. So therefore the maximum possible product in this case is 2 times 3 to the power 658, and this is our answer. So what we did here was a line of reasoning that I just love. It basically investigates the situation by taking a concrete example. In this case, I took the example of 20. I started splitting it to try and increase the product at every step. And as I did this, I realized that I'll end up at 2s and 3s. And I also observed that if I had 3 2s, I could combine them into 2 3s, and that would increase the product even more. And therefore, my maximal set, the set with the maximum product, would have all 2s and 3s, but the number of 2s would not exceed 2. And that was really the key insight, the crux move here. And then I just kind of went about proving these observations, these insights. No element would be greater than 4 because you could then split it like this and increase the product. A 4 could be just split as 2 and 2. And this is actually just a simple simplification just to keep your elements simple, keep them elementary. You want as few elements, as few variations as possible. So that's why we did this. But then we also observed that if you had 2 2s three 2's, you could combine them into two 3's to increase the product. So your number of 2's would never exceed 2, because three 2's could always be replaced. And then we also concluded that no element could be 1, because 1 could combine with any other element and give us a higher product while keeping the sum the same. So using these 4 constraints, we basically kind of applied them to these different numbers, and in each case we were able to find the maximum product. And in our actual number, we found that 1976 is 658 times 3 plus 2. So therefore 2 times 3 to the power 658 would be the maximum product. So that solves this question. It came up on one of the hardest math competitions in the world, the IMO, International Math Olympiad, as you know. But you can see how simple and elegant the line of reasoning is. So this is really the beauty of math. You often encounter problems that seem very hard, exceptionally difficult to crack at the outset. But when you start investigating them step by step, when you start reasoning through them step by step, you find ways to crack the problem open, like we did here by taking a specific example and gleaning some insights that actually helped us finally solve the problem. I hope you enjoyed it. I love this problem for this reason, because it seems very hard, but even very young students can understand and solve it. I hope you enjoyed it as well. And once again, if you have any other way to solve this, if you have any alternative approaches here, do let us know in the comments. Thank you for watching.